Yeah, good afternoon, everybody. Welcome to our first COMPAS seminar in spring 2021, still presented via Zoom, today by Shane Elipot of the Department of Ocean Sciences. And Shane got his some undergraduate degree in Nancy, France in 1998, and then he went to ENSTA Bretagne in France and got a diploma engineer degree, so like a master's of engineering degree in oceanography and hydrography in 2001, and also from the University Bretagne Occidentale in Brest, he got a master's degree of advanced studies in meteorology, oceanology, and environment, also in 2001. Then he went to Scripps in California and got a PhD in oceanography in 2006. And after that, he came here to Miami already in 2007, working across the street at AOML. And a little later in 2008, he worked for RSMAS, still here with us. Then he went to the United Kingdom for a few years, working at the University of Liverpool and at the National Oceanography Center in Liverpool. And in 2013, he came back to Miami, now really as a RSMAS employee, as an assistant scientist in 2013, and then he became an associate scientist in 2014. And then in 2019, he became a research assistant professor. And so now he is still a research assistant professor in the Department of Ocean Sciences. He has 27 peer-reviewed publications. He has 23 other publications. And he is a co-chair of a CLIVAR, a working group of ocean uncertainty quantification. And he is also a co-chair of a CLIVAR panel for climate variability and predictability. So that's his CV, and he will talk about a proposal to use drifters for sea level change monitoring, and you can begin now and start to share your screen.
Awesome. Thank you, Roland. Thank you very much for everybody for joining us today. So let me share my screen. Here you go. All right, we got it. All right, so today I decided that, thank you very much for the opportunity to give me the opportunity to tell you a little bit about this work that I've been doing most recently. I realized that I hadn't given a talk to our department at RSMAS for about 3 years. So I thought it was about time to give you a little talk about something I've been working on. So a lot of the work that the work that I'm going to present is something that I published last year on my own, but several people were very useful and give me a lot of very useful feedback throughout the years, and they're listed at the bottom of this screen. So moving on. So this is a quick outline of what I'm going to talk about today. So I'm not going to tell you about why we should observe sea level. I'm just going to talk about how I think we should observe sea level. And then it bears a question, because we already observe sea level, but why should we need a new observing system for mean sea level? And so that will lead me on to give you a little review of how we currently measure and monitor global mean sea level. Then I'll talk about a proposal, which is devising a new observing system for mean sea level using surface drifters. And these are the results that are described by a publication that was published just a couple of months ago. And I'll give you some conclusions and next step. And before I dive in, I guess it's useful to give a couple of definitions. which I think is very interesting. And I had to think about all these things when I started to think about sea level. So the first one is the mean sea level, which by definition is the time mean of the sea surface, and the sea surface being the time varying upper boundary of the ocean. So nothing very earth-shattering here. But what is important to realize is that you can think of the sea surface as having a given height. So one might talk about the sea surface height, and then you need to define a time period over which to take an average of that sea surface height, and then that defines you a mean over that time period. And this is the quantity called the mean sea level. So as an example, you can think about surface gravity waves at the surface of the ocean not being important for what we think as the mean sea level. Or maybe you may be thinking about oscillatory motion of the sea surface, such as the tides, that you might want to remove from an observation of the sea surface height in order to obtain a time mean sea level. So you obtain the mean sea level in some places in the ocean, and then you go globally and you obtain a quantity called global mean sea level or global mean sea level rise, which by definition is the increase of the volume of the ocean divided by the ocean surface area. So this is really the quantity that we are mostly interested in, or that is of very climate importance. So I give a reference at the bottom of this slide, which is a paper by Gregory et al. In 2019, which talks about concept and terminology for sea level. So I won't be going into the details of that, but I thought that was a very interesting paper to try to wrap my head around the concept of sea level. So why should we observe regional and global mean sea level? I'm not going to tell you about floating at the coast, et cetera, but it's interesting to realize that sea level is identified by the Global Climate Observing System, or GCOS, as an essential climate variable. And so an essential climate variable is a physical, chemical, or biological variable of or a group of linked variables that critically contributes to the characterization of the Earth's climate, right? So just from that definition, what one might understand why we need to measure sea level, okay? And so as an essential climate variable, or ECV, sea level is associated, has a formal definition. And that formal definition goes as follows. The global mean sea level change provides a measure of the net change in ocean mass due to melting of glaciers and ice sheets, changes in terrestrial water resources, as well as net change in ocean volume due to thermal expansion. So from that definition, one might understand better why we actually need to measure sea level. It tells you about the climate. It tells you about the melting of glaciers and ice sheets, etc. And there are two products related to the sea level essential climate variable, and that is the global mean sea level and the regional mean sea level. So how should we observe those products of this essential climate variable? So there's a table that comes in the specification sheet for mean sea level that tells you that global mean sea level should be observed at a frequency of a week or months with a resolution about 10 to 100 kilometers. And the global mean should be known with an accuracy of 2 to 4 millimeters, as well as an accuracy of about a centimeter over a grid point. And when you think about trends or decadal linear trends, GCOS suggests that we should know such a trend with an uncertainty or an error equal or less to 0.3 millimeter per year. All right. So when you think about regional sea level, which is the second line of that table, which might be, let's say, the sea level in the Gulf of Mexico or the sea level, the mean sea level average over the North Atlantic, well, it is recommended that one should look at it on hourly to weekly time scale over a length scale of 10 kilometers. And we should know it with an accuracy of about 1 centimeter. And we should know its trend, its linear trend over 10 years with an accuracy of 1 millimeter per year or less. All right. So just as a point of reference, global mean sea level decadal linear trend uncertainty as measured by satellites, and I'll be talking about that. The uncertainty on the global decadal linear trend varies between 1 and 0.5 millimeter per year. And these are 90% confidence limits, according to a paper published last year. So with altimetry, it doesn't seem that we're actually doing what is necessary according to GCOS. Anyway, just as a point of reference. So then the question you might ask is, like, why do we need another observing system for regional and global mean sea level? So it bears the question, how do we actually observe regional and global mean sea level? So very quickly, the first way by which measure sea level is using tide gauges. So the relative sea level change is a quantity registered by a tide gauge. So it measures the sea level relative to the solid surface where it is attached. So here's an example of a tide gauge on our own pier here at RSMAS. And you can see that it's collocated with a number of other instruments measuring water as well as air characteristics. And you can see on the left some other examples of what tide gauge could look like. So as an example here, it's a radar tide gauge in the port of Alexandria. Here it's a tide gauge in Antarctica, or was it Arctic? I forgot. And this is a time series, the type of time series that you obtain from these tide gauges. And some tide gauges goes back to the beginning of the 19th century. So we have quite a long record of that relative sea level change in some punctual locations. So the tide gauges are great, but they, by definition, they're actually located on the coast, right? So on the left, you see a map of the geographical distribution of tide gauge records that you can find in the Permanent Service for Mean Sea Level database, which is a data center located in the UK. So by definition, they're at the coast. They don't tell you very much about what's happening in the middle of the ocean. And actually, the long tide gauge records, research quality ones, are relatively few. And as you can see on this map, they're biased towards the northern hemisphere. However, the latest tide gauges can record sea surface height at very high frequency. And typically you can get data every 6 minutes. So you can get very accurate, very good, very high precision, very accurate measurements of mean sea level, but they're on the coast. Nevertheless, you can use the record for the individual tide gauges, and you can statistically and geographically integrate all those data to obtain a global measure of global mean sea level as well as its rise. So here's an example from a paper from 2014, where the authors have decided to aggregate the time gauges into different regions, and then you aggregate those different regions, and you get the time series on the right. That gives you the changes of global mean sea level based on the tide gauge record. And you can deduce a lot of things about our climate system based on such records. The other way by which you measure sea level is using satellites. So the geocentric sea level, that is the level of the sea with respect to the center of the Earth, has been measured over most of the global oceans since the early 1990s by satellite radar altimetry. And as I said, the instruments are located, the instruments that is a satellite or the radar on the satellite, are located in a terrestrial reference frame, so equivalent to the reference ellipsoid of the Earth. And they measure their vertical distance from the sea surface, and since you know where the satellite is, you can determine the range, and you can determine the mean sea level from satellite altimetry. So the reference satellite altimetry missions that started in 1993 with TOPEX Poseidon, and then the JASON satellites, and the latest one, Sentinel-6 Michael Friedrich, that was launched last year, have followed tracks that have been repeated through times and that are shown here on this diagram. And they cover most of the global ocean, but they limit to 66 north and south. So with satellites, you can obtain statistics about changes of mean sea level, and such as the trends shown on the left throughout the entire period very accurately. And then you can combine all this data, you can average the data, and you can obtain an estimate of global mean sea level rise since the beginning of the altimetric era in 1993, such as the curves shown on the right. So altimetry is going to tell you about what's happening in the middle of the ocean. It's a reference record. But the effective spatial scale is maybe on the order of 50 to 100 kilometers. And also you can obtain such a global map such as this one. So this is a trend, but you can obtain a global map of the mean sea level throughout the world ocean about every 10 days. So it's relatively low frequency compared to the tide gauges. So you can actually combine tide gauges and satellite records. You can use the information on spatial scales that we obtain from satellite, and you can combine that with measurements from tide gauges. So I'm not going to go into the details of that, but several groups have used the combined information between satellite and tide gauges to reconstruct what the global mean sea level has been since the middle of the 19th century, based on the tide gauges only, combining with the spatial information from the tide gauges. So the two mean sea level record from satellite or from tide gauges are actually complementing each other, I may say. They give different type of information. So then why do we need another observing system? So I propose an observing system that could be global or regional, not only, but also high frequency. So global and regional like the satellites, but high frequency like the tide gauges. And then let's think big. Let's say it's going to be resilient. That is, it's going to be resilient to failures. It's going to be relatively affordable. It's going to be expandable. And it's going to be adaptable to technology or new questions that may arise about sea level and its changes. So how can we do that? So I propose that we could actually do that with the drifters of the Global Drifter Program. So most of you may be familiar with the drifters of the Global Drifter Program. The processing of the data and the deployment of the array is actually managed by our colleague at AOML across the street. And you can see here on the left a map of the status of the array on January 11th of this year. And there were about 1,500 of those buoys. And here you have a picture of how a buoy at sea might look like. And here you have a diagram of the surface buoy of a drifter, as well as a drogue that is attached by a tether to the surface buoy. So it turns out that these buoys used to be tracked by the Argos positioning system that was only able to give you the latitude and longitude of those drifters, and hence deducing their trajectory and the currents at the surface of the ocean. But it turns out that they are now tracked by GPS, which sparked the idea really of what if they actually reported not only the longitude and latitude, but what if they also reported their altitude, their heights over the center of the Earth? Because a GPS position, such as the one you might get on your phone, is actually a three-dimensional position in the reference frame of the Earth. So why don't we use this information if it existed, and it doesn't? Unfortunately, they actually calculate their height, but they don't report that data point to land. But what if they did? And so the rest of the talk is basically a simulation exercise to try to see if by reporting their heights by GPS, the drifters could be used to measure sea level and global mean sea level. So for this, I'm going to use the hourly data set of position drifters as a function of time. I'm going to use version 1.1 that contains about 115 million position of those drifters. And here on the left, you see a number of curves that show you the number of drifters as a function of time since 1993 to the end of 2016. So some of you may know that these drifters start their life by being drogue. That is, a drogue is attached to the surface buoy, but after some time, because of wear and tear, that drogue typically detach, while the surface buoy continues to transmit its position. So then they become undrogue, but they still could be used for scientific analysis. So you can see two curves, the number of drogue drifters, which is in yellow, and the number of undrogue drifters as a function of time, which is here in red. And the total number of drifters is here shown in blue. All right. So what is the concept of this simulation exercise? So I'm going to simulate individual mean sea level measurements in time and space as acquired by a drifter. So a measure, local, punctual, by a single drifter of mean sea level would be basically the height from the GPS sensor receiver on the drifters, minus a reference height, which is basically the height of the mean sea surface. And the mean sea surface in our case is the sum of a surface called the geoid and another surface called the mean dynamic topography. All right, and I'll talk about that in a minute. And then part of the measurements from that drifter would be an error, which is basically SSH variability, which is irrelevant for mean sea level, such as surface gravity waves or tides, let's say. So we have this equation. So I'm going to simulate those measurements. But what I'm going to try to do as well is simulate the variance associated with these measurements. So throughout this talk, I'll be using the word variance or error or uncertainty in the same way. Please, I apologize about that. But basically what it means, if you quantify the variance of that measurement, which according to this equation is the variance of the GPS measurement, plus the variance of the mean sea surface estimate, plus the variance of all the sea surface variability unrelated to mean sea level, plus twice the covariance between the GPS measurement and the sea surface height variability. All right. So let's see how we can go about estimating those terms and simulating those terms. So first of all, simulating sea level or mean sea level measurement from the drifters. Why do I say that it has to be the GPS height minus the mean sea surface? Well, let's assume that mean sea level rise was uniform in the ocean. Then you could place yourself anywhere in the ocean, use a static buoy, let's say, that would be anchored to the bottom of the ocean. And then you could be measuring mean sea level as a function of time, and then you would see the rise of the sea level. Well, the thing is that mean sea level is actually not uniform, right? So this is why you need to measure it in many different places. So if you use a drifter is going to change its location as a function of time, as it's going to be advected by ocean currents. So let's say that the mean sea surface, the sea level rise was uniform, but the drifter, a single drifter, was actually able to drift freely at the surface of the ocean. Let's say it was going to go from the Arabian Sea to, let's say, the Agulhas Current. Then it would basically follow the mean sea surface, and then you would see changes of mean sea level along the trajectory of the drifter that would be on the order of about 200 meters. That's the difference in height of the mean sea surface between those two regions. So what you would measure from a drifter is basically the changes of the geoid and the mean dynamic topography rather than mean sea level rise. So this is why you need to remove an estimate of that static pattern of mean sea surface from every single individual measurements in order to measure locally as a function of time changes of mean sea level. So please note that the same type of issue might affect altimetric measurement, but it doesn't matter with altimetric measurement because altimetric measurements are always taken in the same location at many different locations. So with altimetric measurement, the only thing that you need to do is subtract a mean, and then you can get the anomalies or the changes with respect to that mean. But with a drifter, you would need to measure or have a measurement or an estimate of the mean sea surface as a function of time. Otherwise, you will be measuring the geoid plus the mean dynamic topography, that is the mean sea surface, and you wouldn't be measuring mean sea level changes. So in order to do that, so let's assume we can do that, but let's simulate nevertheless what we can obtain. So I'm going to use a model, and rather I'm going to use an ocean reanalysis that assimilates altimetric measurement as well as hydrography. So it's basically capturing sea level rise. This model is capturing sea level rise that is due to the adding of mass from the melt of ice, as well as the thermal expansion of the ocean. And here you see on the left a map of the sea level trends from that model. And this is going to constitute the truth of my simulation exercise, but we're going to consider that it's the truth, and it's actually very close to what you can obtain from altimetry. And here on the right, you can see a density of those drifter measurements that I'm going to be using. So I'm going to take all the drifter locations in time and space, and I'm going to interpolate the sea level anomaly from that ocean reanalysis. So ocean models actually do not include a geoid in their representation of the Earth's surface, so that the mean of an ocean model is only the mean dynamic topography. So if you subtract the mean dynamic topography from your sea surface height model outputs, effectively you get a sea level anomaly, which is equivalent to getting a GPS height minus an estimate of the mean sea surface. So interpolating in time and space sea level anomaly from your model at the location of the drifters is equivalent to those hypothetical measurements that would be taken at sea. So we're going to take those simulation of mean sea level from drifters, and then we're going to take on daily time step an average, and we're going to get what we call the global mean sea level. And then independently of that, I'm going to be estimating the variance or the error associated with single one of these measurements, take the global average also at daily time step, and obtain that quantity sigma squared GMSL, which is basically the variance of the global mean sea level. And that variance is a function of time as well. So we're going to obtain time series of global mean sea level and its associated error. So I told you earlier that the equation to estimate the variance of these mean sea level measurements is given here at the top of this slide. So it turns out, without going into the details, that when I go into global averages of every one single of these terms, I'm going to rearrange them and obtain the following expression. So the total error or variance of the global mean sea level is going to have four main terms. The first one is going to be a sampling error, which is not appearing in this equation. And I'm going to add this on top, and I'll explain that to you in a little bit. And then it's going to have a GPS error, sigma squared, GPS, which is going to be prescribed, as I will explain. And that comes directly from this term, the variance of individual GPS measurements. And then it's going to have an error that is due to Sisyphus height variability, which is not related to mean sea level processes. And I'm going to obtain that from model estimates. And then it's going to have an instrumental error, which I'll be discussing as well in this talk. And it comes from also some statistical simulation of what that instrument error might be. So in the rest of the talk, I'm going to be going basically through each of those single error terms and then come up to a budget at the end to try to see what we get and if the type of observing system that I'm proposing would be valuable. So first step, the sampling error. And that has to do directly with, I see we have a note in the chat. Maybe that means we have a question. Let's see, someone has to go. Okay, great. So the sampling errors they go as follows. So here on the right, I'm showing you time series of global mean sea level, taking the average of the simulated mean sea level measurements from the drifters, which are given by the blue curves. And then I'm going to compare this to a time series of global mean sea level calculated by taking every single point of the model. So that constitutes the truth. That's a real true global mean sea level from the model. And these are the red curves that are shown here, here on this graph. So the red and blue curves are the daily time series, and the smoothed one are the time series after removing seasonal cycle estimates, as well as smoothing with a sliding window of about 9 months, I believe. So what do you get? I'm looking at this from 1993 to 2015. And what I find is that the RMS difference, the root mean square difference between the two curves, the drifter and the model, is 17.5 millimeter. So that's a very high number. And we don't like that number, it's way too high. And the trends of either the blue curves or the red curves, so the trend over that time period for the drifters is 2.85 plus or minus 0.12 millimeter per year. And for the model, it's 3.30 plus or minus 0.02 millimeter per year. So those trends are quite, they differ according to their error bar, so they're quite different. So drifter is actually not, the drifter array is actually not able to get the right linear trend for global mean sea level. And I believe the reason is because of the following point is that at the beginning of the time series in 1993, we had very few drifters at that time for the simulation exercise that I'm conducting here. And we had a very strong positive bias at the beginning of the time series, so that the trend is actually underestimated by the drifters. What you can see is that starting from 2006, approximately here on this curve, the Global Drifter program reached maturity with an average number of drifters about 1,250. So that's the maturity of the array. So, and we can see that the error has decreased around that time. So let's recalculate those statistics for the last decade of the simulation. That is from 2006 to 2015, and that constitutes 10 years conveniently. So now what we find is that the RMS difference between the drifter and the model for that time period is about 4.4 millimeter. And the trends are basically the same. For the drifter, it's 3.87 plus or minus 0.15. And for the model, it's 3.81 plus or minus 0.1 millimeter per year. So according to these statistics, the two trends are indistinguishable. So the sampling error, which exists, doesn't prevent us from actually estimating the trend over 10 years correctly. So if we summarize this a little bit, we find that the sigma s squared, the sampling error for global mean sea level, is 4.4 millimeter. And the implication of that sampling error for the trend, by looking at the trend of the difference between the drifter and the model, is minus 0.05 plus or minus 0.08. So when you have this bias and this error, this uncertainty, we basically add them quadratically to come down to the conclusion that the implication of the sampling error from the array is 0.1 millimeter per year. That's a consequence of the heterogeneous sampling of the global ocean by the drifters. It exists, it's 4.4 millimeter, but the uncertainty for the trend is only 0.1 millimeter per year. So now, what about the GPS error? So we have estimated that the horizontal accuracy on average for the GPS on the drifters is about 22 meters in the horizontal. But what about in the vertical? Well, we actually have no data. So we can't know what type of variability we have in the vertical from the GPS on the drifters. And also what I discovered, looking at this problem is that GPS is actually a science. Some scientists devote their entire career looking at GPS processes, with application in geodesy or sea level as an example, but GPS is a real science. And GPS data actually exhibit systemic errors, some atmospheric effects, some issues with satellite orbit modeling, with the precision of the clocks on the satellite, as well as on the receiver, the choice of the calculation method, the effect of the sea states in our case. You can understand that the GPS on your phone doesn't exactly have the same accuracy that the GPS that is used, let's say, to reference a tide gauge. Nevertheless, I just wanted to point out that how do we actually calibrate altimetry? Well, we do use GPS at sea. So we use GPS-equipped buoys at sea that can provide estimate of absolute biases between altimetric sea surface height with an accuracy about 1 to 2 centimeters. So the way we do that, we use very big buoys that are actually moored at sea, anchored at sea, such as the one shown here on the right. They have a lot of batteries, lots of instruments, enormous amount of storage. They can get very high frequency GPS data, about 1 hertz. And they use a geodetic grade antenna and chips, such as the one shown here on this 2 figure. So here on the left, I was told, is a Rolls-Royce of GPS antenna that has this specific, design around it so that to limit interference. And then the chip that actually uses, that is that is actually deriving the GPS, coordinates, cost about $1,000, about the size, half the size of my hand, as you can see here on this photo. So we can actually do it, but can we actually do it with small buoys? Well, we're not quite sure. However, technology is evolving, GPS science has evolved, and it is possible actually to measure sea level with a buoy such as the one shown on the right here, which is about the size of a Global Drifter Program buoy. And measurements from such buoys have been compared to tide gauges. And as an example, they found that they could get an accuracy as high or as high as 5 centimeters compared to tide gauge measurements located nearby at 6-minute interval, right? So I believe it is possible, and I'll be talking about that later on, but I'm not going to try to give a given number for the GPS error. On the contrary, I'm going to consider a range of values for the overall GPS error per individual daily drifter measurements. And I'm going to consider a range of random error with a standard deviation from 0 to 2 meters, which I think are reasonable range of error to consider for GPS measurements from a single drifter on daily timescale. So the next type of error that I needed to consider for mean sea level measurements from drifters are errors from variability of the sea surface height that is actually not relevant for mean sea level. So the first one is the variability of sea surface height from barotropic tides and baroclinic tides, such as or internal waves in general. So how do we actually estimate that variance as a function of time and as a function of space? So I'm not going to be able to estimate it as a function of time for now, but I'm going to estimate it as a function of space. And I'm going to use the results of a paper by Savage et al. That was published in 2017, where they produced basically maps of sea surface height variance for a number of frequency bands of sea surface height variability, such as here's an example that shows you the range of the diurnal band, the range of the semi-diurnal band in purple, and the range of superinertial internal wave continual band here showing in yellow. So what I was able to do is that I took the global map, such as the map for the semi-diurnal SSH variability from that model. And you can see that it can be decomposed into a steric component related to internal waves and a non-steric component or barotropic wave component. So I've taken those maps of variance of sea surface height that I've interpolated at all the drifter positions as a function of time, even if those maps were static. And that allowed me to estimate what that variance from tides was. And then I took some global averages and I obtained the following results. So here on the left, I'm showing you, so I'm switching the colors a little bit, I apologize. So here I'm showing you a PDF of all the values of tides and internal wave sea surface height estimated from that model. The median value is about 0.19 meter because it includes the barotropic tide. And here's a time series of that globally average error. So the tides and internal waves in yellow. And you can see that it starts very high on the order of 100 millimeter, but then it decreases as a function of time. And when the number of drifters, n, becomes approximately constant, that error from tide and internal waves seems also approximately constant. So between 2006, it averages to 1.6 millimeter error for the global mean sea level. And another thing we notice is that it's actually correlated with n, the number of drifters, at minus 0.9, meaning that the more drifters we have out there, the smaller the error from tides and internal wave. And we're going to use that to our benefit. The next type of error that we need to take into account for the sea surface height is the error from surface gravity waves. As you can imagine, if you've ever deployed a drifter at sea, you might imagine what happens to a drifter as it goes up and down with surface gravity waves, right? So how much variance do you get for, let's say, hourly or daily measurements from those surface gravity waves? So how do you estimate that? Same thing. I used a global model of waves. I use WaveWatch 3, and I used a global model at 0.5 degree, 3-hour time step resolution. And I got those data sets from the IOWAGA project. And it's described in a paper by Fabrice Arduin et al. In 2011. So same thing, in time and space this time, I interpolate the variance from the surface gravity waves at all the drifter positions. The median value is quite high, is 0.58 meter for the type of instantaneous error that you get from the drifters. However, when you take a global average, the contribution from the surface gravity waves is the blue curve, which is shown here. Same thing, it starts very high, but starting from 2006, you can see that this error remains stationary in a sense. It averages to 4.4 millimeter, and it's also anti-correlated with the number of drifters. The next type of geophysical random errors that we need to take into account is the error from the mean sea surface. So it turns out that we need to consider two types of errors for the mean sea surface. The first type of error that could be described as a bias is basically a representation error or modeling error of the mean sea surface. So it includes the modeling and the methodological biases that are used to estimate the mean sea surface actually from altimetric data. So in order to understand what type of model error one might induce by their calculation, I'm going to consider two mean sea surface products, one called CNS-CLS15 and one called DTU15. Doesn't really matter what they are, but they use the same data, but different methodology. And the other type of error, which is more of a random type of error, comes from the error in the data themselves used to measure the mean sea surface that propagates into the methodology and the method of estimating the mean sea level. And so for this, I'm going to use the time invariant formal error map from one of the two products. I'm going to use the formal error map from CNS-CLS15. So the first type of error from the mean sea surface, the representation error. So here's a probability distribution function, a PDF, a histogram of all those errors. They're in absolute values interpolated at all the drifter position. And the median value is about 8.65 millimeter. The time series of the global average is shown here. And you can see it seems to be very large at the beginning of the time series when we had very few drifters. But when you look starting from 2006, it's become a lot more stationary. And the RMS value is about 0.77 millimeter for the average of 2006-2015. When you look at the random error, you can also interpolate in time and space, and the median value is about 11 millimeter. So when you put it together, the bias on average, which is that representation error, which I'm going to take as a constant for 2006-2015, is given here by this value. And it was on average 0.77 millimeter per year, 0.77 millimeter on average. We're going to take this value as being constant. And for the random error, that changes with time, it's actually very small. And you can see it's this purple line here. And it averaged to 0.08 millimeter for 2006-2015. But it's also negatively correlated with the number of drifters. So the more drifters you have, the smaller the contribution of that error. So the last type of error that we want to consider is an instrumental error. So here's a diagram that shows what I'm talking about. So this is basically the buoy of a drifter. And if you were able to put it apart, you would see that the GPS antenna right now is about, it's a little like very flat patch antenna, but it's located, within the buoy at a location that we can estimate pretty accurately. However, what I learned is that the center of the antenna is actually an immaterial point, which is actually located above an antenna. It's actually, I think it's called a phase center. So in order to determine what is that phase center is located, you need to know that because you need to know the height of your antenna with respect to the actual level you're trying to measure, here, the sea level. So what is the distance between the waterline and your GPS antenna? So if you use only one buoy, you can go into a very high-tech laboratory and you can actually estimate that exactly. If you were to estimate that on over 1,000 of drifters, it wouldn't be very practical. You actually can't do that. So what I'm going to do, I'm going to take the accuracy that we think we know how to estimate those GPS antenna phase centers, which is about 1 centimeter accuracy. I'm going to assign a constant random bias to all the antennas on all the drifters. And I'm going to do that randomly for all the drifters. And I'm going to assume this bias is constant. And I'm going to recalculate a global mean sea level from those bias measurements. And then I'm going to redo that again, assigning a different random bias to every single one of the drifters. And I'm going to recalculate the global mean sea level time series. And I'm going to do that 100 times. In sort of a Monte Carlo type of way. And I'm going to obtain 100 different time series of global mean sea level from the drifters. And I'm going to compare that to the unbiased time series. And the difference is showing by all the gray curves that are shown here on the right. And I'm going to look at the standard deviation of all those curves as a function of time. And this is the black line, which is shown as a function of time. That error from that instrumental bias take the form of a random error if you want, and it averaged to 0.32 millimeter for the 2006-2015 period. And what's good about it is that it's actually, and it is anti-correlated with the number of drifters as well at minus 0.67. So the more drifter you have, by the power of averaging, you actually reduce that instrumental error with the number of drifters. The last type of error that one might want to take into account is a potential bias from surface gravity waves. So as an example, we know from observing drifters at sea, it hasn't been really reported in the literature, but we know that when a drifter is drogued, the drogue is actually pulling under the buoy as the crest of a surface gravity wave passes. So the goal of this animation here is to show you, that's actually to show you the Stokes drift, but it's really to show you that if a drifter didn't have a drogue, then it would be simply bobbing up and down with surface gravity waves. But in effect, when it has a drogue, it might actually be dragged. So that if you were to, let's say, measure the mean sea level or acquire the sea level from a drifter that would be periodically dragged under the crest of the waves, you might be biased toward the trough of the waves rather than the crest of the waves. So how do you estimate such bias? Well, you can, once again, you can try to quantify it. So what I'm going to do is that I'm going to consider that drogue drifters are going to miss the top of the PDF of the sea surface height of the surface gravity waves. So I'm going to use again the WaveWatch3 output of variance from surface gravity waves. I'm going to assume that that variance corresponds to Gaussian distribution of sea surface height, which is a good estimate for sea surface height. And I'm going to truncate the PDF above 1 standard deviation. So that means drug drifters wouldn't be sampling anything that is happening above 1 standard deviation of sea surface height from waves. And I'm going to recalculate the mean measured by such truncated PDF. And I'm going to recalculate the global mean sea level from those drug drifters. But I'm going to consider that the undrugged drifters do not suffer from such a bias. And this is what you obtain here on the right. So what do you obtain, especially in terms of trend? So just as a reminder, the true trend from the model was 3.80 plus or minus 0.1 millimeter per year. If you use all the drifters, as I said before, that are unbiased, you obtain 3.87 millimeter per year. That's what I reported earlier. So if you decide to use drifters that are actually biased, but only the drug biased drifter, you get the purple curve here with a trend of 4.24 plus or minus 0.2 millimeter per year. So you get a very much biased curve because of the surface gravity wave bias. But that comes from a very small number of drifters, about 400 on average globally. So if you use instead the unbiased undrugged drifters only, you get something around 3.72 millimeter per year with an uncertainty that would make it not distinguishable from the true trend. So if you use the unbiased drifters, it would work. So my understanding is that at the end of the day, it comes down to actually measuring mean sea level using the measuring drifters that are actually standardized, that have all the same biases, right? So if you were to mix up drug and undrugged drifters, that is biased and unbiased drifters, you would obtain drifters such as, you would obtain a curve of global mean sea level such as the yellow one here. So what does that mean? It means that you would actually measure a global mean sea level that would drop. And the reason is because at some point during the lifespan of the array, you had more drug sea level, more drug drifters than undrugged drifters. So because of the bias, the potential bias of those drug drifters, we would basically have observed a drop of the mean sea level just from the sole, idea that the drug means drifters would actually be biased. So I'm going to circumvent this problem by simply saying that the impact of the waves, of the surface gravity waves, basically becomes an issue of how many drifters of standardized design we're going to actually be using. So I'll be ignoring eventually this issue. All right, so I've been talking for a long time, but putting everything back together, what is the total uncertainty for global mean sea level? So just before I went through each of the different terms, and the sampling error, the GPS error that I'm going to prescribe, and that GPS error is going to basically go as 1 over n, where n is the number of drifters, and sigma squared GPS is the error for each individual drifters. And then the sea surface height error and the instrumental error, I told you earlier that each single one component of these two terms are actually anti-correlated with the number of drifters. So I'm going to derive a linear model as a function of the number of drifters. So I'm going to convert those two terms into this model, only function of n. And I'm just doing a fit to the observations and the number of drifters, a linear fit. And it turns out that the coefficient of these fits are given here with these numbers. So now when you put everything together, I think I'm losing my, hold on. I'm going to lose, no, I'm okay. Can you still hear me? Yeah?
Yes, yes.
Okay, great, thank you. Right, so putting everything back together, at the end of the day, my error for the global mean sea level is given by this number, which is constant, and by these numbers that are basically just a function of n, the number of drifters, and sigma squared GPS, the prescribed error in GPS error. So, and then we're going to take that error for the global mean sea level, and we're going to look at the implication for the trends, for the decadal linear trend. So all these terms are basically going like this when it comes to the trend. So if you look at simple linear regression theory, if you have an error sigma squared for quantity, then the error on the trend is given by this expression. The trend error due to the sampling was estimated in a way that took into account the serial correlation of the errors, and I didn't talk about that, but it is a constant number, so about the sampling error that we derived earlier. And then we're gonna have to use add a couple of a number of error on the trends as well that I'm gonna be describing in a little bit. So now at the end, the global mean sea level and the global mean sea level trend variance or errors are only a function of the prescribed GPS error and the number of drifters. So there are two types of errors that we need to add for the trend estimates. So I told you that just like altimetry, GPS measurement of mean sea level are given in a geocenter position, are given in the geocentric reference frame. There are some uncertainty in the position of the center of the Earth, basically. The uncertainty for a trend based on a reference with respect to the center of the Earth is about 0.1 millimeter per year. So we need to add this error for the trend of global mean sea level rise, which is what we need, and not the trend of the geocentric sea level rise. So there's another error as well that comes also from going from global mean geocentric sea level changes, which is the same thing that altimetry will be obtaining, to global mean sea level rise. And that is due to the deformation of the Earth. So it is what scientists call global isostatic adjustment, or GIA, as well as a redistribution of mass from contemporary ice melt and hydrology. So those two processes, the rebound of the Earth's crust from the last glacial maximum, as well as the changes of the distribution of mass of water from melting glaciers and ice caps, are basically deforming the surface of the Earth. So it creates a difference between a geocentric mean sea level rise and the sea level rise that we actually care about, which is the quantity called global mean sea level rise in the reference frame of the solid Earth, basically. So those conversions are on the order of 0.2, 0.3 millimeter per year. But what matters here is not the conversion itself, but the uncertainty in the conversion. And the conversion from the convergent uncertainty because of GIA is about 0.05 millimeter per year. And the conversion uncertainty due to ice melt and hydrology is about 0.02 millimeter per year. So when you put everything back together, you obtain the following graphs. So here at the top, I'm showing you a contour plot of the uncertainty from the proposed observing system using drifters of global mean sea level as a function of the number of drifters and a function of the GPS random error between 1 and 2 meters. On the right, I've recalculated everything as a function of monthly time step. So I'm giving you also the global mean sea level uncertainty on monthly time step or with monthly averages as a function of the number of drifters and as a function of the GPS vertical random error. And finally, I'm showing you the uncertainty in decadal global mean sea level trends as a function of the number of drifters and as a function of the random error. So the conclusion here is that considering that the nominal number of drifters from the global drifter program is about 1,200 drifters, which is shown here by the vertical dotted line, daily global mean sea level estimates would always be larger than 6 millimeter, right? So according to this contour graph. So remember, the goal was maybe to obtain something between 2 and 4 millimeter. But I estimate that on daily time scale with the drifters, we would obtain estimates of global mean sea level of at least 6 millimeter and increasing dramatically with the GPS random error increasing. On monthly time scale, we would be doing much better. And we would be measuring global mean sea level on monthly time scale with this new array with an uncertainty less than 4 millimeter, if the GPS random error was less than 0.4 meter standard deviation. And when it comes to the decadal linear trend uncertainty, what I find is that we would obtain a global mean sea level trend uncertainty less than 0.3 millimeter per year if we could maintain the individual daily random error of the vertical GPS measurement from drifters below approximately 1.6 meter standard deviation, sorry. So in summary, I have demonstrated that the global drifter program array could provide a third observational system for global mean sea level. This system could further validate and calibrate, but also complement the other two existing systems, because maybe we could obtain something global at a relatively high frequency, maybe on daily time scale. The system could be regional. For the sake of this talk, I talk about the global estimates, but we could have looked also at regional estimates. We could be covering areas such as the Arctic, which are not covered by the reference altimetric mission. I believe it would be a system that would be comparatively cheaper, resilient, and adaptable as well to the different question one might ask about regional sea level and especially high frequency variability of the sea level. And the current limitation is the GPS technology because it's unknown and we don't know basically how to adapt yet the technology that is used on large buoys for the small buoys. So I told you that in terms of linear trend, it could be acceptable if we kept the error below 1.6 meter standard deviation. So 1.6 meter standard deviation random error for a GPS receiver is actually pretty bad. But because of the power of averaging, we could reduce that for the linear trend estimates to something very, very acceptable. So we're not trying basically to transfer geodetic grade GPS measurement to the buoys. We're trying to see how much we can degrade, let's say, the highest GPS measurements to something that would be acceptable in order to obtain global mean sea level estimates and trends that would be, let's say, useful for climate studies. So in order to do that, I'm happy to report that we have a pilot project that has been initiated with colleagues from NASA JPL, Josh Willis and Bruce Haynes at JPL. And I'm collaborating on this with our colleagues across the street at NOAA OML, Rick Lumpkin, as well as Lucas Santorioni from SIO. And what we're going to do is that we're going to investigate and we're going to see how we can transfer technology from very high-tech buoys to relatively small buoys like the Global Drifter program to obtain something acceptable to measure sea level. And so how we're going to do that, we're basically going to deploy some buoys of the Scripps Pier and of the RSMAS Pier, and we're going to compare that to the type of measurements that we obtain from the adjacent tide gauge. So here's a picture that's showing you what could happen to those buoys. You can actually have some birds deciding to sit on them. So we might have to be careful, but we're not going to have this type of bias when we do our field experiment. What I've done also with colleagues is that we are basically proposing this as an ocean shot concept for the US Ocean Decade launch meeting that is going to happen in February. So if you want to know more about this idea of using the Global Drifter program to measure global mean sea level, maybe you're going to attend this meeting. And if you haven't heard of the US Ocean Decade that just started this year, I encourage you to do so. And I've also talked about, I posted on my website, a lot more explanation about why I think this could be a reliable observing system. And with this, I've talked for a long time. Thank you very much for your attention, and I'll be taking questions if you have any.
Yeah, thank you very much. That was a nice presentation. If someone wants to ask a question, I suggest that you activate your camera and then your microphone so we can see you when you speak to us. Don't be shy. Yeah, Arthur, I knew there would be a question from Arthur. Please.
That was a really nice study, and that's a really good idea. I'm glad you're pursuing it. I'm curious, in your formulas, you call n the total number of drifters. Do you really want that n to be the total number of independent drifters? Because drifters are correlated in space and time.
Yes. So, so for the calculation, I have used the number of drifters per day, right? So that's one thing. So I'm also, for each daily averages from the simulation or for the estimates of the variance, I'm basically averaging 24 measurements first per drifter, right? So that's the first type of averaging that I do. And then you're right. So in the calculation that I've shown, especially when you go from the estimate of the global mean sea level to the trend, right? For the sampling error, I took care of taking into account of the correlation of the sampling error, right? I didn't talk about that. But for the other type of errors, such as the GPS, as well as the Sisyphus height error, it is possible that those errors are going to be correlated. So I might have to revise that. So, that's a point that was brought up by several of the reviewers. The paper was rejected 3 times. I had to, keep persevering. But at the first step, I'm going to assume that these errors are going to be correlated first, because I'm going to basically first averaging globally from those, thousands of locations distributed randomly throughout the ocean. But I agree that the errors for the trend might increase once we consider correlation. And I think that would require a little bit more of details in terms of the correlation length scale of the barotropic tide and the baroclinic tide, et cetera, et cetera. I agree. I think for the GPS error, globally would be okay. But I think for the geophysical random errors, we might have some correlation that might increase the error on the trend uncertainty. I think you're correct.
I agree with what you have to say here. And, basically results would be the same if just you put the word independent in data points. And this is kind of related, is you did a really awesome job of looking at a lot of the sampling biases. I learned a lot from your talk, and some of those issues I had never thought of myself. But I'm just wondering, what is the effect of the fact that we do have preferential sampling by these drifters, for example, based on convergence versus divergence zones, which is fairly large scale? Yeah.
So, I could share with you some of the slides that I have, but yes. So one of the things I noticed, and it's not in the paper that was published last year in GRL, is that one thing of interest is the seasonality as well on regional scales of the global mean sea level. And if you look at the seasonal cycle from mean sea level, as would be measured by the drifters, it's very much biased, let's say throughout the North Atlantic, where you actually have a larger mean sea level seasonal amplitude. So yes, the sampling bias is going to be affecting very much things such as the seasonal cycle. Yet, unless, the model doesn't represent accurately what's happening in the real ocean, that sampling bias from like convergence region seems to be okay, because for the trends, because we still obtain an estimate of the trend that matches, according to the uncertainty, what we obtained from using all the data points in the model. So at the regional scale, we might have to be a little bit more careful, but for the global mean sea level estimate, I think we're okay. Just for the same reason that the Global Drifter Program is actually trying to palliate for those caveats by actually, doing a lot more of deployments in divergence regions, such as along the equator, in the Gulf of Guinea, and things like that. So yes, there's a potential bias, but I think it seems to be okay.
Okay, thank you. And good luck with the project, Shane. Very exciting.
Thank you very much. Thank you.
Okay, any further? Yeah, Lisa.
Hi, Shane. It was a great talk. I really enjoyed it. I'm not one for all the technical details as Arthur, but my question was, when you say regional, that you anticipate that there's, there could be some regional scale. What kind of scales, are you thinking about?
So it didn't make it in the paper, but I looked at 2 other regions. I looked at the North Atlantic between 0 degree and 66 degree north, which is, the highest latitude that the reference satellite record can capture. So I concluded that we could also use, the existing area in the North Atlantic to obtain adequate, regional trends for the North Atlantic. So that would be the one region. And the other exercise that I did is what I call the Nordic Seas, which was basically from 66 north and 80° north, which is not covered by the reference altimetry. And so I was able also to show, so I forgot about the trends because I dropped the regional analysis a couple of years ago, but I was able to show that we could capture the seasonality as well of the mean sea level in that region. So that's what I'm talking about. So ideally, I think this work would be taken further and interrogate the sea level scientists, or try to think about what regionality of sea level we would like to know more about, and try to see and simulate some more measurements in some different regions to try to see what would be adequate. So this is what I mean by regional.
Okay, so you're thinking ocean basin scale. Nice. Cool, thank you.
Yeah, I think that's all for today. So thank you, Shane, again for the nice presentation. Thank you all for coming to our first seminar in this semester. We will not have a seminar this Friday, and we will not have a seminar next Friday because it's our recruitment Friday, but next Wednesday, there will be a fantastic presentation by Brian Mapes on scales and patterns in the ocean. And I hope everybody will come again. So,
all right. Thank you very much. Bye-bye.
Bye-bye.